Today we'll do some more stuff on transformations and generalize what we talked about last class with sine functions and cosine functions. Also, hopefully, we just finished taking a quiz, so you can get that to me soon if you haven't done it already. Also, you're working on Project 6 right now, which is due in a few classes. Today we talk about horizontal shifts of our trig functions, and then we put all of our transformations together in one big sinusoidal bonanza. 2. In previous classes, we have graphed several examples of periodic functions, the height of a Ferris wheel rider, the oscillating temperature in a chemical reaction, the number of hours of daylight in Greenfield. In each case, we made life easy by assuming that the starting point, t equals 0, corresponded to the max, the min, or the midline of the curve. Do we all understand what I mean by this? So if you go back and take a look at the Ferris wheel problem, for example, we had the Ferris wheel was this big circle, and the person started the ride at the far right point. And in the temperature one, in this chemical reaction, I think the temperature started at the minimum and then went up and then came back down. But that made life easy because it started at the min, the max, or the middle. But if instead the Ferris wheel rider started up here like 20 degrees above horizontal, well, that would make it tougher to figure out exactly what was happening with the height of the rider over time. So number 3 says, in this section, we relax this assumption and we allow our sinusoidal curves to start anywhere. By start, I mean where is it on the y-axis? First, a brief review of horizontal shifts. How do the graphs of g of x equals x minus 5 squared and h of x equals x plus 3 squared compare to the graph of the parent function f of x equals x squared? So hopefully we know that this graph right here, x minus 5, is 5 units to the right. So you would take your basic parabola x squared and shift it 5 units to the right. And then this one right here with the x plus 3 is actually 3 units to the left. Number 4, let's graph these functions together. So the first one is y equals sine of t minus pi over 4. Okay, so I'll first start by graphing my basic sine graph. So I'll plot my 5 points. So sine starts in the middle and it's on its way up. And it hits the top at pi over 2 right there, back to the middle, back to the bottom, and then the 2 pi got cut off a little bit, but this right here is our original graph, y equals sine t. And then this thing right here says shift your original graph right by pi over 4 units. So each of these points is going to go over pi over 4 to the right. Now the good news is that each of these vertical lines on the grid is exactly pi over 4. So when we pick that point and move it pi over 4 to the right, it lands right there on the next grid line. And then we take this guy and move it pi over 4 to the right, and everybody goes pi over 4 to the right. Next one is a little bit off the grid. And then we'll connect to these 5 new dots and say that this is y equals sine t minus pi over 4. Next one, part B, y equals sine of 2t minus pi over 2. So this one is tricky because it seems like we should just take the graph of y equals sine of 2t, and we can handle that on its own, and then shift this graph to the right by pi over 2. And unfortunately, it doesn't work. If you want to do this, if you want to graph this thing by hand, I'm going to make the following recommendation. And I'm not really going to justify why I think this is a good idea or why what we just said didn't work, but I'd encourage you to explore on your own if you're interested in figuring out exactly what's going on. But here's my strong recommendation, is that you take anything touching the t in these sine functions and factor it out. So I'm going to encourage you to factor that 2 outside. It's still in the sine function, but factor it off of the t. And then what's left after we factor that 2 out? Hopefully we see it's a pi over 4 left. So let's see if we can graph this thing. So we're going to graph y equals sine of 2t first. And then after that, we're going to shift to the right by pi over 4. Okay, so let's see if we can graph y equals sine of 2t. So again, we'll start by plotting our original 5 points for sine of t. Starts in the middle, going up, down, back to the middle, to the bottom, and then back up to the top. So here's our original sine graph. And then we've already seen this sine of 2t before. We saw it last class. So we know that that's a horizontal compression. We know that it affects the period. And we know that all of the t coordinates get cut in half. So we're going to take each of these 5 special points and we're going to cut them in half, and we'll keep the y values exactly the same. So we did this before. So every t value gets cut in half. And we get those 5 points right there. And then we can connect the dots on this one. And that is the graph of y equals sine of 2t. And then finally, that thing gets shifted to the right by pi over 4. And I just want to highlight that it's this number right here that's the final shift. It is different from this number right here. So that pi over 2 is the, we'll call it the pretend shift. It just, it's not really a pi over 2. It's really a pi over 4 in disguise. So the actual shift is this pi over 4. So let's go ahead and grab each of our 5 points, each of the green points, and shift them to the right pi over 4, which is exactly one of our vertical grid lines. So every point goes to the right by pi over 4. So all those green points shift one grid line over, and then we'll connect the dots here in red, and this is our final graph. Okay, so when we're ready, next page. Number 5, 2 definitions. The horizontal shift of a trig function has a special name. It's called the phase shift. This definition of the phase shift is different from your book's definition. We've been using the word sinusoidal for a while now. Here's what it means. A sinusoidal function is any transformation of the sine function. We're also going to use the word sinusoidal to mean any transformation of the cosine function. So just because you see written down sinusoidal function doesn't mean that you have to use sine. You could just as well use cosine for our class. Number 6, let's put all of our transformations together and graph the following. We'll find the midline, amplitude, period, and phase shift. We'll make our own axes once we decide on an appropriate scale. A, y equals 5 sine of pi times t plus 1 minus 2. Okay, first thing I want to say is that this has already been factored out. That pi right there is already in the front, so it's already in the right form. We don't need to do anything with it. But the first thing to do is check and make sure that that number in front of the t is factored out. So just taking a sneak peek at part B, I know the first thing we're going to do here is factor out that 1/4. But it's already done up here in part A, so we're good to go. Let's see if we can start identifying some things. So we need amplitude, we need to know the period, we need the midline, and we need the phase shift. Okay, so the amplitude is the number in front of the sine function. It's just straight 5. The period is 2 pi divided by b. We'll start using the same letters we've been using. Let's see, so the amplitude we called a, and that's 5. And the period is 2 pi over b, where b is the number touching the t. So 2 pi divided by pi. So the period here is 2. The midline is just the k value. And the k in this case is -2. It's that downward shift of 2. And then the phase shift, so I'm going to ask that you write either the word left or right. So the phase shift happens because of this +1. Does that move left or right? That is a left. And it is a left by 1 unit. So maybe we'll try to color code a little bit here. So that 5 is this 5. And this -2 is sitting out here on the side. And then this left 1 is this business in here. And then the period is related to the pi. This pi right here is what goes in the bottom here. Okay, so we've got our pieces. How about we start drawing the graph? So we know that the midline is -2. So let's go ahead and start there at -2. So I'm going to put a dotted line right through there. That'll be our middle. And then the amplitude is 5. So that means 5 up and 5 down from that. So how about we go 5 up from that, which lands us at 3, and 5 down from that, which lands us at -7. And I'm going to go ahead and draw dotted lines there too. And I know definitively that our final graph is just going to be trapped between the top and bottom dotted lines. It's just going to bounce back and forth after hitting each of these top and bottom lines. Okay, next thing we know is that this thing has been shifted left by 1 unit. So why don't we go ahead and start plotting some things on the x-axis. So our starting point is going to be here at -1. And now I want to figure out where the other important x values are. So what I'm going to do is take the period, which we've already found, and divide it into 4 equal pieces. I do this every time with the period. So the period is 2, we found that up above, divided into 4 pieces every time, and it turns out the important numbers are at 1/2. So that means that the next important number is right here at -1/2. Squeeze that in. The next one is at 0. Next important number is at 1/2. Next important number there is at 1, and it keeps going. But I think we can plot our 5 points. And again, I'd encourage you to really go slowly here instead of just trying to draw it all in one fell swoop. So all we got to do is figure out where this thing starts, and then I think we're good to go. So this right here is a sine graph originally, sine, which means it starts top, middle, or bottom. This one starts in the middle. And it's on its way up. So we're going to start at the middle, which is this midline at -2. And we're going to start it right there below the number -1, which was our starting value because of the shift left by 1 unit. And then it's on its way up. So at the next important x, it's going to be at the top. So we're going to hit that dotted line, the one at 3. And we're going to hit it directly over the -1/2, which is our t value. So right up there. And then after we hit the top, we go back to the middle. And that happens at the next important t value, which is 0. So we're here. And then the next one, we're at the bottom at the next important t value, which is 1/2. So we're down here. And then the next important t value is at 1. And we're back at the middle, ready to repeat. So those are my 5 points. You can see it's a very tall, kind of compressed graph horizontally. So it goes up, comes down, way down, back up to the middle, and then repeats. And we know that the period is 2. So for example, the next time that we are back at the original spot, let's see, so that's at 2, and then the next time is at 3. So if you wanted to, you could plot more points and end up getting back to there by the time you get to 3. Something like that. And so yes, it takes some work, but I think that it's worth the time to really plot those 5 points. You can see how, I try to do it freehand and it looks not nearly as good as it does over here. This got way stretched horizontally. So plotting those points, even though it takes some time, I think increases accuracy quite a bit. We'll check our work here. 5 sine pi t, that's x, plus 1. Close, close, -2. Again, anytime you hit sine, cosine, or tangent, check your mode. We are in radian mode, which is right because we've got some pi thing happening here. And now I want to plug into my window. I want to plug in just the one period that we got before here. So that's from -1 to 1. And then the bottom was at -7 and the top was at 3. And I like to make this kind of tight border around my graph so that essentially every time I graph a sine function, it's going to look exactly the same. It's going to start in the middle, bounce off the top of the screen, bounce off the bottom of the screen, and then back in the middle. And it just looks like that every time because I set my window so that it's this very tight kind of border. If you wanted to take a look at the second cycle of this thing, you could let your window go until 3 for the x max, and then we should see 2 complete oscillations. There's the first one. There's the second one. Part B, y equals 2 cosine 1/4 t minus 3/4 plus 6. Okay, so the first thing I mentioned we were going to do up above, but we didn't need to, is to factor out the number touching the t. So do that first. If we factor the 1/4 out, that's a t. That's the easy part. A little bit harder is to figure out this blank. Hopefully you can figure out that it's a -3. Okay, and now we're ready to fill in the same stuff that we had up above, amplitude and period, midline and phase shift. Okay, so the amplitude is the number in front of the sine or cosine. That's 2. The period is 2 pi divided by b. b is 1/4. So the period here is 8 pi. The midline is the k value, which in this case is +6. And then the phase shift, I want you to use either the word left or right. This is a shift to the right of 3 units. Okay, let's go ahead and start drawing. So let's begin with our midline. Our midline is at 6, so we're going to draw a horizontal line at 6. Okay, so 1, 2, 3, 4, 5, 6. So our midline is right up there at 6. And then the amplitude is 2, so that means 2 up and 2 down from that middle. Represent the top and bottoms of our graph. So it's going to get up there to 8 and down to 4. Let's see, the horizontal shift, the phase shift, is to the right by 3 units. 1, 2, 3. So we're going to start there. And then the last thing we need to find the other important x's is to deal with the period, which is 8 pi. And again, I always divide it by 4, because these are the important x values or t values. So it seems like every 2 pi is when something interesting happens. So, so we started there with a shift to the right of 3, and then we're going to need to go 2 pi to the right. And actually, as I think about it, there's no way for me to get the scale to be consistent here, so I'm going to ignore the fact that I'll have different scales on the 2 axes, and I'm just going to say that 3 is somewhere around there. And then we're going to go 2 pi to the right. So 2 pi is about 6, so we're going to double this distance that we went here. And if we double that distance, maybe we land around here. And then we'll keep going that same amount a few more times. So this first t value is 3 plus 2 pi, and then add another 2 pi to that, 3 plus 4 pi, add another 2 pi, 3 plus 6 pi, and then finally 3 plus 8 pi. And I like to see that 8 pi pop up because we've already decided that that's the period. So if you are starting at 3 and then you just go 8 pi to the right, then you land on 3 plus 8 pi. Okay, so last piece of this puzzle before we plot our points is to think about where it starts, top, middle, or bottom. This is a cosine. Does that start top, middle, or bottom? It starts at the top. So normally it would start right up here. However, this one has been shifted to the right by 3, so it's actually going to start right there. Okay, cosine starts at the top, then it goes to the middle. So the next value is going to be right there in the middle. And then it's going to hit the bottom directly above the next t value, so here. And then we're going to go up to the top, to the middle, and then finally back up to the top. And then connect the dots with a smooth curve. And it would continue in both directions. Okay, so that's our graph. Let's see if the calculator agrees with what we said. Okay, we're still in radian mode from before, so that's fine. Let's think about the window. Looks like 3 and 3 plus 8 pi. And you actually type that right in here, and the calculator will change that to a decimal. And then from 4 to 6, nope, from 4 to 8 is our y range. And we have our cosine starting at the top, bouncing at the bottom middle, and then ending at the top right. And it's kind of the same thing over and over again. I mean, it makes it look like they all look like this, but they don't, right? I mean, if you just did like a zoom 6 on this graph, it'll look quite a bit different because the standard window is not the best window here. So there's the top at 3, but you can't really see what's happening here. So I know that every time I use the calculator to graph it, it's going to look like an ordinary sine or cosine with just one cycle in the whole window, but that's just because of the way I choose the window. Okay, next page. If we're given a graph and we're asked to find an equation for the graph, we need to know whether sine is more appropriate than cosine or vice versa. Examine each of the 4 graphs below and decide whether each graph starts at the top, middle, or bottom. When we talk about the start of a trig graph, we mean its y-intercept. So we actually did this in the video for the activity for last class, but if you haven't seen that yet, you might check out at least the first couple of minutes of it where I talk about this in a little bit of detail. Suffice to say that if you have a graph that starts at the top, then cosine seems like a good choice. If your graph starts at the bottom, then negative cosine, the a should be negative there, that's appropriate. If you start in the middle, then you need to know more. Are you going up or are you going down? If you're going up, then you're assigned with a positive a. If you're going down, you're assigned with a negative a. Let's use that above idea in this next problem. Consider a function that models the height of the tide measured at a dock as a function of time of day. Assume low tide has a height of 40 feet and occurs at 2 a.m. There's a 20-foot difference between the tides, and it takes 12 hours to go from low tide to high tide. Let's find a function that models the height of the water. When we're done, we'll find 2 more sinusoidal functions that model the height of the water. So the first thing I might do here is draw a graph. So let's see if we can get a decent looking picture here, and then we'll start coming up with the equation. So it says that low tide is at 40 and high tide is a 20-foot difference. So I guess that makes it 60 up there. And low tide occurs at 2 a.m. So if we're calling midnight t equals 0, then 2 a.m. would be 2 hours in. And then it says it takes 12 hours to go from low tide to high tide. So I guess that means that at 2 p.m. we're 14 hours in, and at that moment we're at high tide. So we start at low tide at 2 a.m. We go to high tide at 2 p.m., which is 14 hours from midnight. And then I think that means we need to keep going until we get to the next low tide. That kind of makes sense, right? Very next day, next low tide would happen at 2 a.m. the next day. So what is that, 26 hours in? And so we get this sinusoidal graph, but it could be a cosine. And then it continues. I don't know exactly where it hits there. In some sense, it doesn't much matter, but okay, so there's the graph. And now we're trying to come up with an equation for this graph. Now we're actually after 3 different equations that model the height of the water. So let's go ahead and start by thinking of, let's think of this point as our starting point. And so if we think of that as a starting point, is that a top, middle, or bottom point? So it's at the bottom of the graph, so that's a bottom point. So since we're at the bottom, then we're thinking of this as being a negative cosine. And I've left a little space there for the amplitude, but let's go ahead and see if we can start filling in the rest of this stuff. So we know the amplitude is how far it is from the middle, so maybe midline is better to calculate first. So the midline is halfway between 60 and 40, which is 50, which means the amplitude is how far it is from 50 to either 40 or 60, which is 10. And we also need to know, what else do we need to know? We need to know the period, which is 24 hours in this case, which means we can use our fancy formula to find B, 2 pi divided by period, 2 pi over 24, which reduces to pi over 12. So I think we're ready to fill in most of this right now. So we decided it's a negative cosine. So the amplitude goes in the front, that's a 10. Negative cosine of, let's see, the B value goes here. So this is a pi over 12. Then it's t, and then there's some horizontal shift, which we haven't identified yet. And then plus the k value of the midline, plus 50. Okay, so what is the horizontal shift? Well, if we're thinking of this as our starting point, and normally negative cosine would start there, then this graph has been shifted 2 units to the right from where it would normally start, 2 to the right. So how do you shift something 2 to the right? You add 2 in here. So this is 2 to the right. So I think we're done. We've got our equation. It's really easy to kind of mess up and make that a 2 to the left, because you could say, well, I need to take this point and bring it back to the x-axis, or sorry, the y-axis. But that's not how it works. You have to think about your normal cosine and then transform that thing into what you want. So it's always where is it normally, and then how do you get it to where it actually is in reality. So that's why it's, well, except that's not a 2 to the right. So let's fix that. 2 to the right. So t minus 2 shifts at 2 to the right. Okay, so I think that's good. But there are many, many other ways to write the equation of that same green graph. Let's suppose that we now think of this guy as being the start. Okay, so does this one here start at the top, middle, or bottom? So that starts at the top. So let's start writing our equation here, y equals. It starts at the top, so it's cosine. In fact, everything else is the same except the horizontal shift. So the amplitude is still 10. It's now a positive cosine, so it's not negative 10. Bracket here, still pi over 2, pi over 12 for the b. Still a t in there, and then some blank thing for the horizontal shift, and still a plus 50. So there's a lot of commonality here. But now the question is, if you think of your cosine as normally starting at the top here and then going down, how do you take this point and bring it over to this point? Well, we have to shift it 14 units to the right from where it normally is to where it actually is. So how do we shift 14 to the right? We do a minus 14 right there. Okay, let's try one more. Suppose now that we think of this point as being our starting point. Okay, so in this case, are we starting at the top, middle, or bottom? If we start here, so that's a middle point, which means we need more info. It's either a middle going up or a middle going down. Which one is it? This is a middle going down. And so as we saw up at the top of this page, if you're at the middle and going down, then you are a sine with a negative. So all we're going to do is right here in red, exactly the same as what's up there in purple, 10. But now instead of cosine, we said it's a sine, and it's negative. Pi over 12. There's a t, blank space for the horizontal shift or the phase shift, plus 50 is consistent. So question is, what's the horizontal shift here? Well, normally your sine graph would start there and head down if we were a negative sign. So we got to take that point, the normal starting point, and shift it way over here to the right. So I guess we really need to know what this number is right here. Okay, let's see. It feels like that number right there must be halfway between 14 and 26. So is that a 20? So halfway between is 20, so let's label that. And so if we need to shift from the normal spot to this spot right here, that's a shift of 20 to the right. So t minus 20. And so one thing you can do is check all of these on the calculator, y equals. So I'm going to type all these things in and come back when I'm done. Okay, so I think I've typed those in correctly. Now we're going to think about the window. So the window that we want is just the window that's going to capture this behavior. So basically from 2 to 26. I guess we could start at 0 if we wanted to. So let's go from 0 to 26. And then as far as the y's go, it looks like all the action happens between 40 and 60. So you could go 0 to 60 if you want to. You could also do 40 to 60. Okay, now if we've done this correctly, then the first one will graph exactly like we expect, but then the other two are going to be right on top of the first one, and we won't be able to see anything. So here's what I'm going to do instead. I'm going to first turn these off by just hitting the enter key when I highlight the equals. So you can see that one's off and this one is on. So I'll hit enter right here, and now they're both off except the first one. So let's see if the first one gives us what we expected. A little bit of a dip, then it reaches the top of the window. It comes down, and then right there in the middle, or at the bottom, I should say, at the end here. So that's looking good. So here's what you can do. We're going to turn this thing back on, but now we're going to come over here, and this thing right here is the standard graphing icon. If you hit enter, it makes it thick. We'll do that on the last one. Hit enter, and it talks about shading above or shading below. I want the one that looks like a key, that one right there. So if we hit graph, then we should be able to see that little circle tracing out the graph. And so it should land perfectly just on the graph that already exists, and that looks good to me. So it's a nice way to confirm that, that the second equation we came up with matches perfectly the first one that we talked about. So this is fine here, and then we can do one more, and that one more involves turning this guy on. So hit enter right there, and then hit the left arrow, we'll hit enter and make it thick. And then we'll hit graph, and we should see it thick graph, the rest, or the curve that we've already seen up there. So that's nice to see that all three of these different looking equations we came up with all perfectly match this graph, and there are many other equations that perfectly match this graph. You might push yourself a little bit. All of these involve right shifts, but you might think about what the graph looks like over here and see if you can find one or two left shifts, that is things with plus signs in the parentheses here, that will again land perfectly on that graph. All right, the activity is here. Give it a shot before you check out the answer key or the video.